Section 2.2 talks about just not a problem. Let's keep this that. So there we go. 2.2 talks about evaluating determinants by row reduction, and let's talk about that a bit. So here we're going to start with few definitions. It says if you have A to be a square matrix, again the number of rows equal the number of columns, n by n. If you have a row of 0 or a column of 0, then automatically you pick that as the you pick the cofactors of that, and you're going to get the determinant to be 0 guaranteed. If you have a square matrix, the determinant of A and the determinant of A transpose is the same. Now this is very important. Let's say you have an m by m matrix. If B, so this is matrix A, if B is the matrix that results when a single row or a single column is multiplied by a k, then the determinant of B, so if you take A and you multiply either a column by A or a row by A, simply the original determinant of A will be multiplied by that k. That's it. So determinant of B is when you multiply, let's say, a row of matrix A by k, it becomes matrix B because it's no longer the same. The determinant of the new matrix is simply the determinant of the previous matrix times A. If the B, so if what you did to A was you took two rows or two columns and you interchanged them, then the determinant will change from positive to negative. And if B is the matrix that results when you multiply a row of A and add it to another row in A, any multiple, then the determinant doesn't change. So if I have matrix A, which is A, B, C, D, I'm going for 2 by 2 because it's simple. If I multiply by K, if I say I have KA, KB, CD, right? If I call this B, the determinant of B will be whatever the determinant of A is, you multiply it by K. That's all there is to it. And if I took matrix A again, and what I did was I wrote CDAB, call that B. Now, the determinant of B is negative determinant of A. And if I multiply this row by any number and add it to that row, the determinants don't change. Now, they go ahead and they include that slightly, but for elementary matrix, remember, elementary matrix is when you have one operation only on the identity. So 1, 0, 0, 1, you apply just one modification. If E results from multiplying the identity matrix by K, then it's the same thing. Determinant of E is K because the determinant of this is already 1. Determinant of the original is 1. You just multiply it by K, then that becomes K times 1. And if you interchange the rows, it becomes negative 1. And if you multiply this row by any number added to that row, the determinant doesn't change. And again, the determinant's right there. And if you have 1, 0, 0, 0, 1, 0, 0, 0, 1, that's a diagonal matrix. The determinant of that is simply the product of those, which is 1. It's not saying anything new. And lastly, I want to talk about if you have a square matrix A with proportional rows or column, that means if I have here A, B, and here I have C, A, C, B, whether it's row or column, if you happen to see that this row is a multiple of that or this column is a multiple of that, then the determinant of that is automatically 0. You don't have to show any work. So first we want to verify that the determinant of A and the determinant of the transpose are the same. Well, if this is A, the determinant of A is simply 12 minus 2, which is 10. And if I write the transpose of A, switch the rows with columns, then if I find the determinant of that, that would simply be 12 minus 2, which is 10. Again, that doesn't change. According to the theorem, that works well. Here you could just show it. But to really work on the rest, we need to verify those. The next problem, we say find the determinant of the given elementary matrix. Remember, this is elementary. That means you originally had the identity. So the only way to get a 5 right there, it would be if you were to multiply this by -5 and add it to the bottom. And we already agreed that that doesn't change a thing. If you call this A, then the determinant of this elementary, actually let's not call it A. If it's elementary, let's call it E. The determinant of this elementary matrix is simply one that doesn't change. Remember, you could multiply a row by any number and add it to another row. Here, we notice that you multiplied, so this is kind of what well, for now, let's just write it out, not a big deal. We say determinant of this elementary matrix would simply be -1/3 times 1, because you must have multiplied a row 2 by a third, or column, doesn't matter, but let's go by row. So the determinant of that would be simply be -1/3. And that's kind of what you have to eyeball as you move on. Now the next problem, evaluate the determinant, and again, this is not something that we know. Well, give me one. Oh no, I went off. So right, here we go. I just went to another section. I meant to do this. Okay. Evaluate the determinant of the matrix by first reducing the matrix to raw echelon form and then using your combination of row operations and cofactor expansions. Well, this is what we're going to do. We're going to really go for a triangular matrix. Let's see how that works. So first, I notice the top all have a 3. I'm going to take a 3 out of that. So take k out of that. So let's write it right. I want to find the determinant of 3, 6, -9, 0, 0, -2, -2, 1, 5. What I'm going to do first step, take a 3 out. That will make this 1, 2, -3, 0, 0, -2, -2, 1, and a 5. Then what I'm going to do, I'm going to take twice row 1, add it to row 3, put the result in row 3. Well, 2 plus -2 is 0. 4 plus 1 is a 5. And -6 plus 1 is a -1. Now, if I take a row 2 switched with row 3, I'll pick a -1, and I'm looking at 1, 2, -3, 0, 5, -1, 0, 0, -2. Now, what I'll do, I want to make that a 1. So 3, -1. I'll take a 5 out. 1, 2, -3, 0, 1, -1/5, 0, 0, -2. Then what I do, I'll take a -2 out. And I'm looking at a triangular matrix. In which all of these entries are 1. And if you multiply those ones times that, you simply get positive 10, 30. Now, it wouldn't work out the same way if you were to leave the 5 and the -2. Here it's a coincidence, but normally it doesn't. This is the way to go. I look at the following and I want to work out the same thing. Now, assume that that's not a matrix. I'm looking for the determinant of this. In this case, my first step would be take row 1 times 2, add it to row 2, put the result in row 2, take negative 5 row 1 plus row 3, put the result in row 3. Multiply row 1 by 2, 2 plus 2 is 0, negative 6 plus 2 is negative 2, and 0 plus 1 is 1. And if you multiply row 1 by negative 5 added to 5, that's 0. 15 minus 2 is 13, and 0 plus 2 is 2. Now, at this stage, it would be very important for me. Again, I know it sounds like the same thing, but it's not. To take that negative 2 out. Make that 1, negative 3, 0, 0, negative 1, positive 1, negative 1 half, 0, 13, and a 2. Then I want to make that a 0, and the way to do that, you would take negative row 2, add it to row 3, put the result in row 3. So I have a negative 2 already. 1, negative 3, 0, 0, 1, negative 1 half, 0. If I multiply this by 13, negative 13, I didn't even write that. There we go. If I multiply that by negative 13, I'll get negative 13 plus 13 is 0. I'll get 13 over 2 plus 2 for 17 over 2. And now, if I take negative 2 and I take 17 over 2, I'm really looking at, and it turns out not the same thing if you are to leave it at the end and at the end factor. It doesn't work that way because that one doesn't affect the determinant in any way. Since all of these are ones, oh come on, I took the 17 halves out. It turns out to be negative 2 times 17 halves times 1, which is negative 17. Now, of course, once you got it this far, you could have said take this row and multiply those if you really want, and that works out the same way. But if we want to follow along, that's really how it works. And now, if we know that the determinant of this matrix is negative 6, if that's known, we would like to know what would happen here. Well, let's see. What did they do? They swapped those two. If you switch a row or column, what would happen? So they switched row A with row G, it seems. So wouldn't that determinant be minus a negative 6? And that determinant will become a 6. And that's all we want to do here. We want to make sure that we can apply these properties properly. And how about here? Here, I'm trying to figure out what did they do. So I noticed that, first things first, they multiplied row 2 by a negative. So that gives me a negative 1. And now the matrix looks like this. And it seems the only other thing they did was they added this row to this row. You could add and subtract any way you want. So that's the only thing that's going to change. And the answer will be a positive 6. And if I look at number 20 to try and figure out what did they do, well, let's see. First, they multiplied row 2 by 2. So I could take that 2 out. That clears those two. And then it seems they took G and they added that to 3 times A. So that means that doesn't change anything. The determinant will simply be negative 12. And let me see if I could shift that just a bit to the left and fit the last one in. Let me see how big is that. Okay, the back one can't fit in. There you go. And 22 is the last problem. Let me see what they did to 22 if possible. It seems it seems on number 22, oh, they multiplied this by 2a and they put it there. Isn't this a multiple of that? That means that determinant will become simply a 0 because the third row is a proportional of the first. I'm gonna shift a few things around really quick, and there it is.